Hey guys, it's Margot at Lanterna here. Welcome back to another Analysis and Approaches IB Maths video. Today we're going to be moving on with integration and looking at a second part, which is 5.16 of the higher level syllabus, and we'll be looking at integration by substitution, which is an incredibly powerful method. So let's have a look. Okay, so what is integration by substitution? Integration by substitution is a method of solving integrals of a very specific form, and that form is given here on the slide. So we're solving integrals which are in the form of a function of some other function g of x times the derivative of our function g of x dx. And there's a stepwise method in which to solve these integrals, which I always really found useful when I was doing my IB, and I find that other students find really useful as well. So let's just quickly talk about those steps, but the most important thing is just really knowing how to apply it. So we're going to be doing lots of examples after this. So our first step is usually, well, we need to identify what is our function g of x, and we call that a function u for simplicity, and therefore what is our function f of u. So what is really important here is that you know the different integrals in the formula booklet. The second step is to compute the derivative of our function u with respect to x. Then what we do is we substitute that function u and du into the integral to then be able to solve the integral with respect to u rather than x. So by identifying this function and its derivative and making a substitution for u, our aim is to essentially simplify this integral to make it into something that we know how to solve, i.e. some of those common integrals which are listed in our formula booklet. Finally, then, we need to remember initially they did ask us to solve the integral in terms of dx, so we just need to make sure we substitute our expression for u in terms of x back into our solution. So let's have a look at an example. First of all then, we've got the integral of 3x squared plus 5x all to the power of 4 times 6x plus 5 dx. So what you need to do is you need to pick out a function and its derivative. So we see that 6x plus 5 right here is actually the derivative of 3x squared plus 5x. So that's a good starting point. What we said in our method, we had to identify this function u and our function f of u. So u then, u is, in our case, 3x squared plus 5x. So that our function f of u is this entire thing, 3x squared plus 5x all to the power of 4. Then our second step is to compute the derivative of u with respect to x. So let's have a go at that. Du by dx, using our differentiation rules, is 6x plus 5. And what I'm going to do is I'm just going to rewrite this in a slightly different form. I'm going to say du is equal to 6x plus 5 dx. So our second step is to substitute u and du into our integral. Well, how do we do this? Well, what we've recognized is that we've got our function u right here, and having rewritten our derivative of u with respect to x as du is equal to 6x plus 5 dx, we see that this whole thing right here is du. So if we make that substitution, we see that we can rewrite this as the integral. So this is step 3. This was step 1, step 2. We can rewrite this integral as the integral of u to the 4 du. Substituting in our function u and du. And this is an integral we know how to solve, right? Remember that in our formula booklet, we get the equation for the integral of x to the n. Well, that's exactly the same here, right? It's just a different integration variable, but that doesn't make a difference. We're essentially integrating with u rather than, with respect to u rather than x. So if we integrate this using that integration rule, we find that this is equal to u to the 5 over 5, and because this is an indefinite integral, always remembering that integration constant c at the end. Okay, so we've now solved our integral. 4 is sorry, that was step 4, and step 5 is to now substitute our expression for u in terms of x into this solution. So if we substitute this, we see this is going to be equal to 3x squared plus 5x to the power of 5 over 5 plus c. So this is our final answer. So let's just look over what we did there and why this is such a powerful method. So we identified a function and its derivative. We computed the derivative of that function. We substituted our function u and du into our integral such that the integral that we're now having to solve is a lot easier to solve, and we can do it using those equations given to us in the formula booklet to work that out, and then finally just making sure we substitute our expression for u back into our solution. Good. Okay, so that was one example. Let's have a look at another example. Next example then, cube root of x squared minus 3x times 2x minus 3. Okay, so if you want to have a go at this before we go through the solution, pause the video right here and have a go. Okay, so let's think about, we need to identify a function u and its derivative, or a function of a function u and then the derivative of u. Well, we identify here that 2x minus 3 is the derivative of what's in this cube root, right? The derivative of x squared minus 3. So our first step, we've identified that u is equal to x squared minus 3x. Second step then, computing the derivative of u with respect to x, we find that du by dx is equal to 2x minus 3. Again, I'm just going to rewrite this as du is equal to 2x minus 3. Why do I do that? Well, it's just to make that substitution that we're going to do in the next step even more explicit. So now we are making the substitution. We see that this is our function u, and right here we have our whole du. So if we make that substitution, we find that this is equal to the integral of the cube root of u times du. Now, again, this is an integral that we're able to solve using the formulas in our formula booklet, slightly less explicit than the last one. Why? It's because we need to know that we can rewrite the cube root of u as u to the power of 1 over 3. So remember, if we have the nth root of any function, this can be written as that function to the power of 1 over n. So that's a really important one to remember. So this is our integral of the cube root of u du, using now our formula for the integral of x to the n, or u to the n, it doesn't make a difference, right? We see that this is equal to the u 1 over 3 plus 1, so that's going to be 4 over 3, divided by 4 over 3, plus c, and I'm going to say this is equal to, just rearranging this, 3u to the 4 over 3 to the divided by 4 plus c, leaving our final step to just substitute in our expression for u, which is x squared minus 3x to the power of 4 over 3 over 4 plus c. So this is our final answer. So again, just working through those steps in that method one by one to get us to our final answer. Good, let's have a look at another example then. Okay, so we've got a fraction right here. Again, pause the video if you want to have a go at this yourself. We see that the derivative of 3x to the 4 minus x cubed is equal to what we have in the numerator. So one, we identify our function u to be equal to 3x to the 4 minus x cubed. So if we now compute du by dx, now the last couple times I would write du by dx to then take the dx over to the other side. I'm just going to do that all in one go now. So this is equal to 12x cubed minus 3x squared times dx. So I've just done 2 steps in one there. 3, then substitute u and du. Well, we see, right, that we have our function u here in the denominator, and we have our whole du being everything in the numerator. So if we make that substitution, we're going to get that this is equal to the integral of 1 over u du. For computing that integral, then this is equal to ln of u plus c. So using, again, the formulas listed in our formula booklet to then find that finally, making that substitution, this integral is equal to ln of 3x to the 4 minus x cubed plus our integration constant c. So again, what we've done is we've turned this quite tricky, messy looking integral into something that's really neat and tidy, and which we should be able to recognize as one of the simple integrals which we can find in our formula booklet. So a really powerful method. Okay, so finally, I want to have a look at a slightly trickier example. So really just building it up by one step. That is this example right here. And we're going to see why this is a little bit different, and it's going to require a little bit more work than the other examples that we've done. So the reason why this one is slightly more tricky is because identifying u and du is not quite as simple as in the last cases. If we look here, we have essentially 2 options to choose from for u. We could choose x to be u, or we could choose 4x squared plus 1 to be u, or even e to the power of 4x squared plus 1 to be u. Well, let's just consider all of those 3 options and see whether they're going to make any sense. So if we were to choose x to be u, then we know du by dx would be equal to 1, i.e. du would be 1, but then we wouldn't, if we were to make that substitution, nowhere would we account for the e to the power of 4x squared plus 1. So that's not an option for us, right? Okay, well, in that case, we could have the whole e to the power of 4x squared plus 1 to be our u. If we take our derivative du by dx, well, that's going to be something times a function e to the power of 4x squared plus 1, remembering that the derivative of e of x is equal to e of x. And there's no other e of x in this integral, right? So that wouldn't make sense either. Well, then let's look at our final choice, which is u is equal to 4x squared plus 1. Well, in that case, if we'd chosen that to be our u, then our du is equal to 8x dx. Okay, so we see that we're actually partially there, right? Because what we have is, well, we have an x in the integral. What we don't have is this 8, the coefficient of 8 in front of our x. We don't see that anywhere in our integral. Well, that's okay. How are we going to solve that? Well, we can rewrite this integral, and I'm going to show you how we can rewrite this integral. Rewrite the integral to allow us to make that substitution. I'm going to rewrite this as follows. Well, we want there to be an 8x dx, right? So what we want is we want there to be an e to the power of 4x squared plus 1. What we had originally was just x dx, but what we'd ideally want is there to be an 8 in front of that x, right? If we had an 8 there, we would have absolutely no problems at all solving this integral, but we don't, and we cannot just put it in there because it's going to change the value of the integral, right? Well, there's a really nice trick to get around that, and that trick is to multiply this integral by 1. And what do we mean by that? Well, as I said, we cannot just multiply this integral by 8 because it's going to change its value, but we can multiply anything by 1 without changing its value. So what we're going to do is we're multiplying this integral by 8 over 8, which is 1. And what we're doing is we're taking that 8 inside the integral, and we're leaving the 1 over 8 outside the integral, because now what we have is we've got that 8x dx we can substitute for u. So let's see how this works. We can say, then follow step 3 and substitute in our integral now e to the power of u du, because remembering right here we have our function u and here we have our function du, so we're making those substitutions. Now we know what the integral of e to the x dx is, right? So we know what the integral of e to the u du is. So if we solve this integral, this is going to be equal to 1 over 8 e to the u plus c. So therefore, step 5, plugging in those numbers, then the function u, we're going to get this is equal to 1 over 8 times e to the power of 4 x squared plus 1 plus c. Good, so why was this one different? Well, because we couldn't substitute du in straight away, we had to do a little bit of work to be able to get that du in. And what we did is we multiplied our whole integral by 1, right? But instead of multiplying by 1, we multiplied by 8 over 8 because we wanted that numerator 8 in the integral, so then we could leave our 1 over 8 outside the integral. So I'm just going to make a note of that here, multiplying by 1. We get the desired form. So that was it for integration by substitution. I hope you found that useful. It's an incredibly powerful method. The best thing to do to learn it is to just do lots and lots of practice. I'm going to be back with more videos later. In the meantime, check out our website or our YouTube channel to find some more videos in other subjects. But for now, I hope you have a great day and I hope to see you again soon.